If you're staring at an upcoming exam on electrical motors and the equations are starting to blur together, take a deep breath. We are going to walk through the DC series motor in under 5 minutes, so you can walk into that test with total confidence. To understand the math, we have to look at what this machine actually does. When engineers need to drag thousands of dead weight from a complete standstill, they turn to this specific motor design, because it produces massive torque exactly when the load is heaviest. That pulling power comes from how the machine is wired. In a series motor, the stationary magnets, called the field winding, and the spinning part in the center, the armature, are connected end to end, forming one continuous line. It works like water flowing through a single pipe. Because these parts are connected in a series, there is only one path for the electricity to take. This single-path design is the reason the motor behaves the way it does. Because the same electricity travels through every part, the magnetic strength and the mechanical push are linked together perfectly. This diagram shows the connection. Follow the line from the supply, through the field coil, into the armature. With one path, total current I equals both field and armature currents. This bottom equation shows internal voltage is supply voltage minus energy lost pushing through resistance. The magnetic pull inside the motor, which we call flux, depends entirely on this shared current. Because the field coils are part of that same single line, more current automatically means a stronger magnet. Since the electricity stays consistent across every component, controlling the current gives us a direct and predictable way to manage the motor's total power output. Now that we have the circuit down, let's look at the mechanical muscle the motor produces, which we call torque. This is the twisting force that actually turns the wheels. In a series motor, the relationship is exponential. As this boxed note shows, the torque is proportional to the square of the armature current. This graph illustrates that squared relationship. Because the torque grows exponentially, a small increase in current results in a massive surge of pulling power. This is exactly what you need to get a heavy load moving from zero. Eventually, the curve straightens out. This is the saturation point, where the iron magnets are full and can't produce any more magnetic pull, causing the torque to grow at a steady linear rate instead of an exponential one. That initial exponential surge is why these motors are the standard choice worldwide for moving heavy loads that would stall other types of engines. However, that same design creates a specific risk we have to account for. If we look at how fast the motor spins, the math changes. This section of the notes explains the speed characteristic. Here, speed, represented by the letter N, has an inverse relationship with current. When the current is high, the speed is low. But if the current drops, the speed goes up. Look at the left side of this chart. If you remove the heavy weight from the motor, it needs very little current to spin. With almost no current, the speed curve shoots nearly straight up, climbing toward dangerous levels. We see the same result on this speed-torque graph. When the torque, or load, is very light, the motor's speed becomes incredibly high. These overlapping charts demonstrate the standard mechanical trade-off of the series motor. It provides incredible strength, but it requires a constant heavy weight to keep its internal speed from spiraling out of control. This leads to a common exam question and a vital safety rule. Never start a DC series motor unless a physical load is already attached to it. Without a weight holding it back, the motor accelerates so quickly that centrifugal force causes internal parts to fly apart, destroying the machine in seconds. Because of this, you'll find these motors used in heavy industrial applications where a massive load is always present, such as construction cranes or heavy-duty lifting hoists. They are also standard for electric locomotives. The train's massive weight ensures the motor always has something to pull against, keeping it stable and safe. By starting your study with that single loop of wire, you can accurately predict the current, the graph shapes, and the safety rules. Master that one connection, and you'll be ready for any series motor question on your exam.